Hello, good morning, everyone. This is the second lecture of our course, and let me share the iPad. Okay, so this lecture, we basically will start discussing what we call in the theory of superconductivity, the macroscopic quantum model. Let me put here lecture 2. And here we use these letters. So, sorry, macroscopic MQM. Okay. So the idea of, as I explained yesterday, well, a detailed explanation of the microscopic behavior of superconductivity is for that you need of course using the BCS theory, no? So for a microscopic of superconductivity, I mean all that has to be with normal superconductors, okay? So low temperature superconductor, essentially. Here we have a BCS theory. And within this theory, what we have is the concept of Cooper pairs. So the idea here is that well, essentially the superconductivity is a quantum phase transition, second order quantum phase transition, and meaning that you may develop a order parameter in your system, and which, I mean, you can treat the theory of superconductivity using, for instance, the Landau theory for phase transitions, which is a generic theory. And in that theory, you use the concept of order parameter. And the order parameter corresponds to in that theory, we refer to as charged superfluid, essentially. And you may develop all the theory of Landau and study the thermodynamic properties. Even you may be able to have famous Landau equations as well. But I mean, for that case, it is the key concept is that all the particles, essentially we have electrons, but when you cool down the sample and you across a critical temperature, then what was observed was that the system behaves, enters a superconducting state, and and then from the microscopic point of view, you have here the formation of Cooper pairs, where Cooper pairs, they have opposite spin, but also opposite momentum. Okay, and then then the Cooper pairs are bosons. Here, so we have bosonic particles. And when at the critical temperature, then below the critical temperature, then all those bosonic particles, they condense. Okay, we have a condensate where all the particles, all Cooper pairs, will stay in exactly the same ground state. Okay, so this is the typical idea. I mean, this is the state that you expect when you have a condensed. I mean, a condensate. Let's say it could be a Bose-Einstein condensate, or even here in the superconductivity also as well. We have a condensate. So in the ground state, because we have bosonic particles, it means that you can put many particles in a single state. Okay, because there is no this restriction of Pauli principle. Okay, and then it means that you can think about the wave function for describing the condensate as a macroscopic wave function, essentially. Okay, so indeed, if we use this concept of a macroscopic quantum wave function, which I mean is the key tool for this macroscopic quantum model, in fact, we are able to demonstrate or prove many of the collective behavior that appears in superconductivity. I mean, on the emergent behavior of a superconductor. We will be able to explain the appearance of superconducting currents. With superconducting currents, persistent currents, you can explain the Meissner-Hölzenfeld effect. I mean, the perfect diamagnet. So, and even more, you can also explain the fluxoid or flux quantization for when you have a superconducting ring and you have some external flux there. We will see that we can prove that the flux, the magnetic flux, is quantized. Okay. For all those emerging behavior, it is enough to work with this macroscopic quantum wave function. But I mean, what is hidden or something which is the underlying physics is that you have Cooper pairs that are bosonic particles. Then you can condensate all the particles to the same, exactly the same ground state, so that you will have the idea of a macroscopic wave function. Okay, we know this already, okay, but let me put you this a little bit in context. Indeed, well, previous to this macroscopic quantum model, there were a phenomenological theory called the London theory for explaining most of the electromagnetic behavior of superconductors. Okay, in particular, that phenomenological theory allowed to explain the Meissner-Hölzenfeld effect, for instance, with the typical decay of the magnetic field inside a superconductor. Okay, but that theory was developed by I mean, this is the London. This is called the London theory. This theory was published in 1934, and the reference is this is Fritz London. 1934. And this is a physical review article. Only physical review. At that time, there were only this physical review. 379. So this theory, this I don't know why I cannot different color here. This is a phenomenological theory. Based on the observations, London developed this theory that, I mean, of course, he tried to describe the emergent behavior of electromagnetic behavior of a superconductor, and he developed a tailor-made theory for describing the main experimental results. But then by this year, by say in 1948, Fritz London indeed was able to show that the same London equations he proposed in this phenomenological theory could be derived from more fundamental ideas. So Fritz London realized that superconductivity is inherently a quantum mechanical phenomenon. Quantum mechanical phenomenon but the idea is that this quantum mechanical phenomenon manifests itself on microscopic scale in the same way we were talking previously, so that we know already that we have a condensate of Cooper pairs, which are bosonic particles, and all the particles, those bosonic particles, occupy exactly the same ground state. So you have many, indeed trillions of quintillions of Cooper pairs occupying exactly the same ground state. So in that sense, this is a macroscopic quantum phenomenon. That means, of course, we have, this is the important concept that appears here in condensed matter, emergent phenomena. In the sense that, I mean, this is a very complex system. Although we know that there are some Cooper pairs described by the macroscopic theory, but what emerges, the macroscopic behavior, you really can describe this like a charged superfluid, where all the bosonic particles occupies exactly the same ground state. So here appears also the concept of charged superfluid. This concept is also useful when you treat the superconductivity using the Landau theory for phase transitions. There is also the Landau theory is a very general theory for describing phase transitions. So in particular, this is a second order phase transition. It's a continuous phase transition. And in that theory, Landau used the concept of charged superfluid for describing this microscopic object that have some, you know already that the superconductivity, I mean, whenever you have some external action, be electromagnetic field, there is an effect, no, in the behavior of the superconductor. So for sure, because you have this type of behavior, it means that it's a good idea. It's a good tool to think that the superfluid that we are trying to describe is it has some charge. Okay. There is also a theory of superfluidity, for instance, superfluidity, but without including any charge, of course. This is also included in Landau's theory of phase transitions. So the main idea then of this macroscopic quantum model is that we have a macroscopic wave function. So one introduces the concept of a macroscopic wave function. What is the assumption that we have here is that the many-body state, so we have many particles, of course, we have many Cooper pairs. So the many-body state here is described by a collective wave function. A collective wave function. And this wave function, in this wave function, we have, this is the position, x1 will be the position of the one Cooper pair. We have the position of a second Cooper pair, etc., until n. So we assume that we have n Cooper pairs in the ground state. And of course, here we introduce some time dependence into the wave function. Okay, this is important because, of course, there is some dynamics in the behavior, in the emergent behavior of a superconductor, and then this is why we introduce this the idea that we don't have say the wave function may evolve, basically. Okay, so the idea of here is that we have the proposal is that this bar, this function here, this function corresponds to the wave function of a single Cooper pair, but then we have a product state, something like this. This wave function, let's say xi of t, describes the wave function of a single Cooper pair. And so that the macroscopic wave function we have here, this psi, is nothing but a protostate. So meaning that this is in condensed matter physics, this approach is like a mean field. Mean field approach. So we have a separable state essentially. There is for people that knows more or less quantum information theory, we don't have entanglement between different Cooper pairs exactly. Okay, but instead we have you see that there is exactly the same wave function here for describing any of the Cooper pairs that form the superconductor structure. And then this mean field approach is very common when you have a condensate. This is very useful when describing Bose-Einstein condensation, for instance. You also propose a wave function like this. And in that case, what appears is the famous Gross-Pitaevsky equation, which is a nonlinear Schrödinger equation exactly for describing the dynamics of the mean field. This field that we are introducing here, which is the macroscopic wave function. Okay. So again, when you cool down the sample, in the superconductor, electrons pair together, forming this Cooper pairs with, for instance, in the case of a S-wave superconductor, meaning we have that the spin of the Cooper pair is 0 because we have spin 1/2 up, spin 1/2 minus 1/2. So in total, we have spin 0. So this is a boson, of course. And then when you cool down the sample, all the Cooper pairs goes to exactly the same ground state, will occupy exactly the same ground state. So because you have bosons, you can collect many of them. So that a good approach, I mean, when you condensate, when we have this condensation of Cooper pairs, let's say, and then you expect that the wave function is a good approximation to have the wave function in this way as a product state of exactly the same wave function for each of the Cooper pairs. Okay, and indeed, what is quite common to assume this is just the thing that I will write right now. It comes only from purely intuition, physical intuition. So in this macroscopic wave function approach, when you have many of the Cooper pairs that occupy a single quantum state, the ground state, we introduce a new field that contains all the information about the density of charge, as well as the flow distribution. So in general, for describing the whole superconducting state of the system, we introduce the concept of this. This is the macroscopic wave function now, in general. that has to be with, here we introduce let me write down this equation, and then I will explain the meaning of this equation. So here, this wave function, this is a macroscopic wave function where the amplitude has to be with the square root of the density. This is this quantity ns is nothing but the density of charged particles. So let me call this is the density of carriers. It's nothing but the density of Cooper pairs. Okay, this is the proposal. Charge carriers. So Cooper pairs. And this is nothing but we introduce the concept of a superconducting phase. This is famous superconducting phase. Notice that if you take the norm of this wave function, this has to be with the density of charge curves, exactly. Okay, so then of course, the interpretation here is that, for instance, if we put in this way, so imagine we have a volume element here. You can interpret this quantity here as the probability to find the condensate in a specific position x, between x and x plus some delta of volume at time t. I mean, probably this is the something that you realize that this proposal of the macroscopic wave function that we have. So this macroscopic wave function is, it appears purely from our physical intuition. And the physical intuition is, we have bosons, Cooper pairs, that, and all the Cooper pairs, because we have a condensate, then all the Cooper pairs will occupy exactly the same ground state. So you have many particles in the ground state. So that you think about this, introducing the concept of a macroscopic wave function that has to be with the density of charge currents that is included in the amplitude here, but also we should include some superconducting phase. Of course, this is a wave function, macroscopic wave function. In general, because we are treating this as as realized by Fritz London, superconductivity is essentially a macroscopic quantum phenomenon. Then of course, we have to describe the situation using a wave function. A wave function is a vector in a Hilbert space, so that in the field of complex numbers. So this is why we need to include superconducting phase here. I'm not sure whether there is some comments or questions at this very moment.
No.
I mean, probably this is the tricky part, but it comes from purely in physical intuition. Okay, you have to think in that way. You see that there is no constructive way. I mean, from a bottom-up approach. No? So we know that there are some microscopic particles when we cool down the system, but there's always an emergent behavior because these are very complex system. And the emergent behavior it is very successful if we introduce the concept of the macroscopic wave function. Notice that if you take a look, I mean, I will pass in my notes. There is also in my notes, there is also the description of Landau theory for describing superconductivity. In Landau theory, there is the concept of a order parameter, and the order parameter is there is a correspondence with the macroscopic wave function. Although notice that in the Landau's theory, the order parameter is just describes the ground state without any time evolution. Okay, but I mean, including the time evolution here is just justified by agreement with experiments and okay, because you have some dynamics, you observe some dynamics, and then if you propose this and then you go and compare with what you will see in the experiment, this is a good proposal. I mean, it's a good answer to have. It's a kind of this macroscopic wave function is like a time-dependent order parameter, if you want to think about it in that way. Okay. So okay, so from here now, this will be the main concept that we will introduce, and we'll work with this macroscopic wave function. So something that I don't know why. Something which is important. Typically, we will assume that the density of charge carriers is approximately uniform in space. That ns x of t in principle, okay, is uniform. Throughout most of the material. So essentially what I'm telling here is that we will assume that this charge density, this density of charge carrier will be essentially homogeneous. And this assumption here has to do with the following thing. I mean, in the superconducting material, the superconductor material, we have a charge neutrality. Okay, so the material is not an ion. I mean, we have charge neutrality, which is charge equal to 0. So you have in the lattice you have ions, positive charge, but then the material is surrounded by Cooper pairs. Okay, so that the Cooper pairs distribute on the samples such that they cancel all the positive ions of the nucleus in the lattice, so that in a very good approximation, the superconductor effective charge is 0. Okay, and the way to think about this is that it means that you have an homogeneous distribution of Cooper pairs on the sample. Okay, this is why we assume this condition here. I mean, sometimes you will see later that whenever we have capacitors or superconducting islands, where you may include, in fact, this is something that we will see later. So we will have a piece of metal here, which is that we will call a superconducting island. This is the typical situation that we will see when creating quantum bits using superconducting material, in particular the Cooper pair box. So una isla superconductora, superconducting island. Here in this superconducting island, we can put some Cooper pairs, for instance. So imagine we have a Cooper pair like this, or you may remove Cooper pairs. This can be done. This can be done using some external voltages. I'll show you later, okay? So in principle, you may put some, introduce an excess or remove Cooper pairs into the island so that, I mean, this assumption is not valid. I mean, it's not homogeneous. You change a bit the charge, okay, of the superconducting island. But if you compare this change with the whole bulk of the superconductor, where this situation is embedded, you see that still assuming that this density of charge carrier to be homogeneous is a very good approximation, even though, okay? But keep in mind that there are situations where we can remove or we can put excess of Cooper pairs into the island. Okay, so this is a very interesting thing that we will see later. But I mean, this change of imagine. So we have imagine that you put one extra Cooper pair, but one extra Cooper pair as compared with quintillion of Cooper pairs in the sample is nothing. Okay, so to a very good approximation, we assume that this density of charge carrier is constant, homogeneous. Something that now comes more technical part. I mean, of course, this is everything. This is here's technical part. But now we want to describe the dynamics of a superconductor using this macroscopic wave function. The dynamics then, the dynamics of the macroscopic wave function of course, if this is a quantum phenomenon, for sure that the dynamics of the wave function should be the one of course, the Schrödinger equation. So here we have the Schrödinger equation. For a charged particle. A charged particle in the sense that we have a charged superfluid, okay? And of course, that the Schrödinger equation is the following. So, but here notice that this is the macroscopic wave function, okay? And here we have, so let me introduce the concept of Howling. This is ms, is the mass of superconducting electrons. Okay, so this is twice. I mean, in a good approximation, this ms is twice the electron mass. Okay, because we are neglecting any normalization of the mass because of the interaction with the lattice. Okay, but so to a good approximation would be twice the electron mass. And we have the momentum. So linear momentum, but because we have a charged particle, there is also this a minimal coupling. So the particle, this superfluid particle, will couple to the vector potential in this way. So here, this quantity so here we have this charge QS again. To a good approximation, we assume this is twice the electron charge. Okay, and A is some vector potential. But plus, so here we have plus, because we have a charge superfluid, there is also a coupling to the to some scalar potential. So everything, so how this, okay, this sum continues here, and then everything is applied to the microscopic wave function. This is the typical situation when we have imagine a quantum mechanical particle with some charge, okay, and then because we have charge, the dynamics of the particle is described by the Lorentz force. And then here we have the motion equations is ms x dot. So this is the acceleration. So this is a force, of course. Mass times acceleration will have a force, which is the Lorentz force. And here we have, of course, one component of the force has to be with the electric field, but also we have US, the velocity of the particle cross. This is the outer product with the magnetic field B. In the notes that I have here, that I'll pass later after this lecture, there is an example, there is an exercise where you can really prove that. So this is an exercise that will appears in this case. So if you use this, we have a Lagrangian description using the Lagrangian. The Lagrangian that we use is ms over 2. This is the kinetic energy plus some k qs, the velocity times the vector potential minus qs, the scalar field. You may compute the Hamiltonian. The Hamiltonian of the system, and then you can really prove that I mean, this is the momentum of a particle as a single particle, And because when we have a charged particle, we notice that this P appears a change in the momentum that has to be with the charge of the particle. That in this case is the charge twice the this is the that would be the charge of a Cooper pair times the vector potential, and this is the minimal coupling. And of course, you can really prove that the Hamiltonian of the system is nothing but 1 over twice the Cooper pair mass. And then here appears the momentum to the square, but the momentum now has 2 components. This goes to the square plus QS times the scalar potential P. Okay, and here in this part, so essentially this is the momentum here. But of course, here we replace P. So this P is h bar over I and the gradient. Okay, this is what we use here. Okay, so I leave this as an exercise. So using this Lagrangian, compute the Hamiltonian, and you will see that there appear this minimal coupling. Okay, so I stop here a bit because what I would like to discuss a bit more. I mean, so right now then, so again, we have the concept microscopically Cooper pairs. Cooper pairs, you cool down the sample, critical temperature, below critical temperature, then you have a condensate. And the condensate is made of Cooper pairs. So this is why the superconductivity, the equations for describing superconductivity are analog to the one of any Bose-Einstein condensate. Okay, so then all the particles condense into the exactly the same ground state. So you have trillions of Cooper pairs occupying the ground state. So then this way appears the concept of macroscopic quantum phenomena. Okay. And then for that, we propose this wave function, the wave function we have here. So notice that this equation we have here. So you see a single X. This is like right now we are describing the system like a single Cooper pair. But I mean, of course, there are many. But this you can think about this in terms of the center of mass, I mean, okay, of the collection of particles. But then this is enough for describing the whole situation, the whole emergent behavior of the superconductivity. And then so we have this proposal, this macroscopic wave function in that way. So square root of the density of charge carrier times some exponential of some superconducting phase. And then what we need to know, I mean, what rules the dynamics of the microscopic wave function will be the Schrödinger equation, of course. Time derivative of the macroscopic wave function. So everything will appear here. All the dynamics of superconductivity, we will derive those dynamics, be the electromagnetic behavior response of the superconductivity. We can really understand path dynamics using this Schrödinger equation indeed, but with this ansatz for the macroscopic wave function. And here you'll see later, we will compute now the superfluid current, okay, superfluid current, and then when studying the dynamics of the phase, you will see that we can relate the change of the phase, change in time, with some observable quantities as the voltage, for instance. So this is really an interesting thing to look at. Okay. So let me continue. I know maybe that this is maybe, as I mentioned, I always mention this always. This is the tricky part, but everything appears consistent in a physical point of view. I mean, in a physical way of thinking, because you have many particles in the ground state, so that you propose those this macroscopic wave function. Let me talk about a bit on the superfluid current. So one property that we will study in superconducting circuits, indeed, is the charge distribution. So the charge distribution of this superfluid, charge superfluid, we introduce this notation rho, x, and t. This is analog as in electrodynamics. So we have a charged particle. This is the charge of the particle, which is a Cooper pair. And then we have the probability density. Of course, this is a probability density. We know already that this probability density has to be with the density of charge current. Okay. So this is the charge distribution, and because we are talking about superconductivity, this is a superfluid charge. So, of course, this superfluid charge includes very large background of Cooper pairs that compensates, I mean, the charge of the ions in the lattice, the structure. Okay. So, of course, as we know already, we are assuming this charge density is roughly speaking, homogeneous, so that we have charge neutrality in our superconductor. And I mean, here we apply exactly the same concepts we have in your course of electromagnetism, because if we have some charge distribution, we can also define a superfluid current. a superfluid current that we call this J of X times T. And this describing the flow of charges. And because you have a charge distribution and then you have you may define a superfluid current, there is also a continuity equation, of course, like in electromagnetism. So imagine you have a volume here where there is a surface where you have some charge density inside, and then of course you may define so imagine this is a normal vector to the surface, and then there appear you may define the superfluid current flowing through the surface of this volume. So essentially, as in a continuity equation, if you have any change of the charge distribution in a volume, it means that something has to flow outside the surface. And okay, and this is the superfluid current that we have here. So have a look. In the total charge that we have in within this volume, of course, so this charge is nothing but the integral the volume of the density of charge. And then if you have the time derivative, the qt, so any change in the charge distribution, meaning that something will flow outside the surface, you know, through the and then you may be able to define some superfluid current. So here we have, if we take the derivative, so assuming that the volume is fixed, so we have a derivative of rho, yes, and then this should be equal to some flow that appears through the surface. So this is ds is some element of the surface. This minus sign here means that I mean, for instance, if we put this minus sign here and then we put plus sign here, so this minus sign means that we are diminishing the charge. So imagine that we are diminishing the charge into the volume, and then something has to appear outside through the surface. That has to be with the superfluid current. Okay, so this is the equation that we have here. So this will lead us to the continuity equation, because we can use the divergence theorem. Okay, so this is equals to the integral in the volume of the divergence of this a vector field in mathematical terms. The vector field is the superfluid current. And then, of course, you have the continuity equation. So the partial derivative with respect to time of the charge density equals to minus the divergence of this vector field, which is nothing but the superfluid current. And we need to prove right now that we will prove that this current, let me put the expression. This is I, complex number I, QS, H bar, or twice MS. The wave function, the gradient of the wave function conjugate minus a wave function conjugate gradient of psi minus QS to the square ms modulus square of the wave, a macroscopic wave function times the vector potential. This is we will call this the superfluid current. Okay. And this superfluid current indeed allows us to explain many effects, such as, for instance, the Meissner-Hotzenfeld effect. You will see that this superconducting current, you will be able to establish a persistent current in your system, in your superconductor. So whenever you have the superconducting current, persistent current on the surface, it will expel out any magnetic field that try to enter the sample whenever you are in the superconducting state, of course. Okay. And of course, if we have this superfluid current, which is a current density, of course, imagine that now we have a wire here, a superconducting wire. So imagine that this is a wire, and then we have a surface here, and then we have some normal vector to the surface, and then we have a superconducting current. Of course, the current will be nothing but the integral on the surface of this superconducting superfluid density current. Okay. Technically, this is superfluid density current. So I will stop here, and then, because I need to compute this quantity, which is a bit, I mean, it's a bit long calculation. I'll show you this once in my life for you, okay? And then you may continue. I will go through more quick, more fast. But this, I think this is important to do this calculation in very details. So I'll show you this tomorrow. Okay.
Okay.
And then we continue with the discussion of the superconducting phase, and we will see that we will relate any change in the phase with the scalar potential. Okay. So this is will be very important, because then we will establish the equation of motions for describing the dynamics of a superconducting sample. Okay. But again, in this lecture, then the main concept that I introduced was the concept of the macroscopic wave function. Okay. So keep in mind this, try to think a bit more, and but the physical foundations for that is that we have Cooper pairs. So we have plenty of Cooper pairs in the ground state of the system. And this is why we are, it's a good approximation to have a macroscopic wave function in this way. But then you'll see that it's a very good approximation. I mean, it's a very good answer because it will appear the London equation. Exactly, same way. And the concept is that we have a macroscopic wave function, but that obeys the laws of quantum mechanics. So, is there any comment or question?
Yeah, I have a question.
Yes.
When you describe electromagnetic fields, are you consider an external electromagnetic field or internal?
Both, but in this case, it will be the internal electromagnetic field. Or sometimes, well, it depends. It depends because if you put some external magnetic field, you have to put in my hand. But most of the time, I will be describing for instance, how it behaves the electric field inside the superconductor, for instance. Okay.
Okay.
And the superconducting phase for the superconductor, for instance, as well. How the superconducting phase changes. But here we have what you see here. This vector potential that appears here is made. I mean, you have some external source for this vector potential, but also here, because you have. I mean, when you have a superconducting sample, you put between the electrodes, you put some voltage difference, something that comes from the outside, okay, you know, and then you see how your superconductor, the response of the superconductor under the action of external mechanisms, be a magnetic field or an electric field. And then we will see the response, okay, inside the superconductor. But you have always to think about that you have some external sources, but then you try to describe how the superconductor will respond, okay?
Okay.
This is the idea. More comments, more questions?
No, not really.
Okay, Felipe, so see you tomorrow then.
See you.